All right, it is 12, 13, 19. Okay, so today what we're going to do is we're going to graph polar equations and check for symmetry. So before we do anything, test for symmetry with respect to theta equals pi over 2. So if I go back to my unit circle, pi over 2 is here, right? So it's really like the y-axis. So if I were to take a look at a polar graph, right? Pi halves is here. So something that would be symmetrical with that might be one of our cool looking little flowers. Right? Remember yesterday we looked at a cool flower like this. So a graph like this would be symmetrical with pi halves, right? If you were to flip it over pi halves, it's like really, it flips over the y-axis, right? So the test is this. If you plug in and change r to negative r, you change theta to negative theta, and if you can simplify it to come back to the original, then it is symmetrical. We'll also graph it and look at it, but the test is this. So we're going to replace my r with a negative r and my theta with a negative theta for my test. This is only to test to see if it is symmetrical. So I'll rewrite this as a negative r equals 2 sine of negative theta. Okay? How am I doing? Now, last chapter we had some identities. And they were the odd even identities. And we learned that if you had a negative theta, it makes the sine negative. Cosine didn't. Tangent and sine, if it's a negative theta, we bring the negative up. Cosine didn't matter. Okay, so what I can do, it's an identity from last chapter. We can rewrite this as a, bring out the negative, negative 2 sine of theta. And then if I just multiply by negative 1 or divide by a negative on both sides, multiply by negative 1 on both sides, then I wind up getting it back to the original, r equals a positive 2 sine of theta. So if we can make our substitution and modify it so it goes back to the original, if I can make the r negative and the theta negative, and if I can manipulate it some way to make it back to what it looks like originally, then it has symmetry. So we can say yes, this one has symmetry, so yes, it has symmetry over the theta equals pi half. So let's take a look at it anyway. Let's just graph it because it's kind of fun to take a look at these. So if I take my original 2 sine of theta, let's graph it. See what it looks like. Okay. And there it is. Now I can make it a little bit bigger. You guys want to make it a little bit bigger? Okay, so I can go back to my window. If I want to change my window, it's all squared out. But if I can go to my, let's go negative 3 to 3 and another negative 3 to 3 and graph it, okay? Okay, and again, it's a circle, isn't it? So if I were to take this circle, just like Skylar will, and spin this circle around the whole pi half, it's symmetrical, isn't it? You can just see it. Yes, so yeah, Skylar, yeah. Okay, all right.
When you had the smaller circle at first, what happens if you press zoom in and zoom in? Will it just do the same thing?
Maybe.
And then changing the window?
Yeah, maybe. Yeah, probably. Oh, you want angles. You want to go 0 to 360 degrees. Make this be your negative 3 to 3. Want to make sense already? Now try it. Okay?
Thank you.
Yes, you're welcome. Do you know what you graphed? Think about this on a circle. You graphed from negative 3 degrees to 3 degrees. That's all the graph you saw. So does that make sense? That's all you got? Yeah. Okay. All right, let's take a look at the next one. Okay, now, respect for the polar or the x-axis. So let's take a look at an example. Okay, if I had a graph that looked like this, and you can get graphs like this, okay? So this is symmetrical with both, but it's also symmetrical with the x-axis or the theta equals 0, okay? This is like theta equals 0, okay? So if I want to make sure it's symmetrical with respect to the x-axis or theta equals 0, well, the trick is just make r and theta negative, okay? So to do that test, I'm going to go r equals 1 minus 2 cosine of negative theta. So just replace theta with negative theta, okay? Now, if you go back to the ideas we learned last chapter, cosine of negative theta is just cosine of theta. It is. You can look on your identities. Cosine of negative theta is just cosine. And all that reasoning comes from the unit circle. But you probably don't want me to go back to that. But it's true. You know, cosine value here is the same as cosine value here because it's the x, okay? So I can rewrite this as r equals 2 minus cosine of theta. So yes, it has symmetry. Yes, has symmetry with theta equals 0, okay? Or the x-axis, or x-axis. So again, if I graph this, let's see what it looks like. Y equals, I'm going to graph this, clear. 1 subtract 2 cosine of theta. Let's see what it looks like.
Mr. Davies, I'm going down to the office.
Okay. That's not what it's supposed to look like.
Mine looks like that too.
Oh, yes, that is. Yes, that is what it's like. Yeah.
It's a croissant.
I think they call that a limicon.
That doesn't
There are
look-
names for all of these. I think they call it a limicon. But you can see that definitely it's symmetrical over the x-axis, right? Kind of cool. I think they call that a limicon. All right. There's one they call a cartoid because it looks like a heart. Okay. And last but not least, if I have it replaced with the origin, so for instance, let's say I had something that looks like this. Okay. It's not symmetrical with the y. It's not symmetrical with the x, but if I spin it 180 degrees, it'll spin onto itself, right? So this is symmetry with the origin, okay, or 100-degree turns. So we're going to replace r theta with negative r theta, so I rewrite as a negative r squared equals 4 cosine of 2 theta. And of course we know r squared and negative times a negative is positive. So the test works. We get r squared equals 4 cosine of 2 theta. And yes, this original is just like the original. This simplified version of it is the original. So yes, we have symmetry. Yes, we have symmetry with the origin, okay? All right, so those are tests. Now, let's take a look at it, because, I mean, I'm sure a lot of you are sitting there going, why don't you just graph them, Mr. Davis? It's so much easier to just graph it. But some of these tests you have to do in calculus, okay? This is called pre-calculus, so my job is to get you ready for calculus. So we clear that, and the original is, so it says r squared, so let's go square root, if I want to graph this, square root of 4 cosine 2 theta, right? Let's graph it, see what it looks like. Okay. Okay, now, if you spun that 180 degrees, what would happen?
Same.
Same. Now, what if you did the negative part of it? Because it is plus or minus. And I did a negative. See if that adds anything to it, right? 4 cosine 2 theta. Let's graph the negative part. And it might just graph over onto itself. We'll see. A lot of times they do. I think it's just graphing onto itself. But just backwards, believe it or not.
Mine is a different color.
Does it graphing it backwards?
Yes.
Isn't that weird? It goes just the opposite direction.
It just turned from the
So instead of, so the only difference the negative does is instead of going like this, it just went. Right, Zoe?
That is
You probably
right.
saw it, right? Yeah, it's kind of cool, isn't it? Okay, turn the page. This is not too bad. This is kind of fun. You guys kind of like this. Okay, now, all right, grab a calculator. Change the mode to polar. Let's graph some of these. Let's see what they look like. Okay, y equals clear, clear. Okay, all right, you guys do this one. Let's see what it looks like. Okay, 4 cosine of
We did this one.
2 theta. Okay. Oh, did we do this one?
Yes.
Okay, let's do this one real quickly and let's have some fun with it. Okay, graph. Okay.
Oh wait, that looks different.
I'm gonna have to make my.
It's very big.
Yes. What do I need to fix?
How do I turn it to theta?
Just hit the x variable. If you're in polar mode,
Theta.
yeah. Okay, how do I make it bigger? I gotta see. Huh? Window. What do I change my window?
Taller.
So what do I change on my window?
X.
My x min, x max, and my y min. So we gotta go at least 4, right? So let's go out to maybe 5. Okay, so let's go to 5. So let's go to -5 to 5, right? And -5 to 5. If I graph that, let's see what that looks like, okay?
There we go.
There you go. Cool. Okay, now, how many petals does this have?
4.
Now, 4 makes sense to me because every time we do the unit circle, there are 2 values, right? Does that make sense? So in this case, we're going to get 2 petals per quadrant, but then if we go all the way around the circle, we get 2 more petals. So if we want to have fun with this graph, let's add some petals. How would you add some petals?
By changing the 4.
Well, the
Changing
4
the
just
2.
make it shorter bigger. So let's change the 2. How many? Let's change it to 3 and see how many petals you get.
We get 6.
Right, it makes sense, doesn't it?
Oh wait, I only got 3. Never mind.
Only 3. Okay, so then let's go back. If you want 6 petals, what would you do?
And let's pick a 6.
Let's put a 6 right here and see what happens. 6. Graph. Let's see what 6 does. Oh, this is so much fun. Wow, isn't that cool?
A lot of petals.
That's a lot of petals, isn't it?
It's a daisy.
I know. I know. So I'm thinking that maybe Wednesday before vacation, that maybe the assignment would be I'm going to give you these to graph in color and make look beautiful. Because there's some absolutely cool graphs, okay? All right, let's do the next one. How do you graph the next one, okay? So if I go clear, I go 4 plus 3 cosine of theta. See what this one looks like.
We might need to make it.
I graphed 4 cosine 2 theta and gave me a little line on the right.
Oh, look at that. Okay, now I can't see all of it, so how am I going to see more of it?
Zoom out.
Or go to my window. Yeah. Now what am I going to change in my window so I can see more of it?
The X.
The X max, right? So let's go to the window. Let's change the X max to maybe, I don't know, let's try 8, okay?
Oh, perfect.
So the name of this one's called a cartoid because cardiac means heart.
It does not look this.
And so they call this a cartoid because it kind of looks like a heart,
Looks like an
doesn't it?
apple.
It's a really, really bad shaped heart.
Yeah. So there's names for all of these, okay? All right.
To an apple.
So here's our assignment today. And look at the names of the curves. So we're going to do 7 to 15, odd, 19, 33, 37, 43, 47.